today's video, we're going to talk about the last topic that we'll cover from chapter 2, which is section 2.4, the arc length and the surface area. So we'll find the length of a curve where we have y equals f of x, and then the length of a curve where we have x equals g of y, and then the last thing, we want to evaluate the surface area for a solid of revolution that we have. Okay, so let's start with the arc length first. Before we start, let's define what it means for a function f to be called smooth. So if I have a function f that's continuous, if I want to call it a smooth function, it has to be differentiable, and the derivative of the function f, which is f prime, it also has to be continuous. So now if we want to find the length of a curve for a smooth function f, we can use line segments along the curve and add them up to approximate the length of the curve. So for example, if I have the curve of f in the blue here, and then I take line segments between points that are my partition, if I'm able to find the length of these lines and just add them up, that would be an approximation for the length of my curve. So now how do we find the length of these line segments? So let's look at one of these line segments and let's call it L. Now this L would have a horizontal distance delta x and a vertical distance delta y. So when we have these distances, we kind of create a right angle triangle there. So now this piece L is just the hypotenuse in my right angle triangle. So to find the length of it, we just use Pythagorean theorem and take the square root of delta x squared plus delta y squared. If I take delta x as a common factor, I'm going to get something like this, just for simplification. And then by the mean value theorem for continuous functions, I know that there is a point in this subinterval where the derivative at that point is just equal to the difference of y over the difference of x, which is what we have here. So to write a general formula for the length, I can write it as delta x, the square root of 1 plus the derivative of xi all squared. So now this is the length for one of the line segments. Like let's assume it's this one here. To find the arc length for the whole curve, I'll just add the lengths of each line segment. So I'm going to get this sum. Now this is a Riemann sum. So the arc length in general, if I take the limit, would be just the definite integral of the square root of 1 plus f prime all squared. So that's it. This is how we get this formula. So to summarize it, an arc length for any y equals f of x, if I have a smooth function, which means I'm able to differentiate my function and get a continuous derivative, then the arc length from point A to point B is given with this definite interval. So let's try with an example like always. If I have this curve f on the interval from 0 to 1 and I want to find the arc length. To find the arc length, the first step is always find the derivative of your function. So I'll just find the derivatives using the exponent rule. If you simplify, you're going to get just 2x to the 1/2. So now the arc length is just the integral on your interval from 0 to 1, the square root of 1 plus your derivative, and you square it. And now that this is simply from 0 to 1, the square root of 1 plus 4x dx. Now to evaluate this, I can use the u substitution. If you take your u to be 1 plus 4x, you're going to get from So if x is 0, you use 1. If x is 1, you use 5. So from 0 to 5, the square root of u times du over 4. So this is just the square root of 5 over 4. Oh, sorry. I forgot to differentiate. So now I'll have u to the 3 over 2, 2 over 3 from 0 to 5. And just plug in upper minus lower, you're going to get 5, 3 over 2 over 6 minus 0. Now similarly, if I have a function in terms of y, and I want to find the arc length of that, it's the same exact thing, but we're taking the derivative in terms of y, and we're integrating in terms of y on the bounds of y. So if I have this function, for example, first step is always find the derivative. You can find it using either the quotient rule or the power rule here. And then the arc length is just the square root from it, not the square root, sorry, the integral from 1 to 4, the square root of 1 plus your derivative squared. So this is the integral from 1 to 4, 1 plus 1 over y to the 4th dy. Now, we haven't learned yet how we can evaluate this integral. We're going to learn more about it in chapter 3. So you can just leave it like this for now. Now, the second thing that we're going to talk about today is the surface, the area of a surface of revolution. So there's a whole kind of proof in the book. It's a bit lengthy, so I did not write it. I don't think it's important for you to know everything about it, but you can read it from the book if you're interested, and if you have any questions about it, feel free to email me and I can explain it. Now, if I want to find the surface area, we have this formula. Again, your function is going to be smooth. Since I want to find a derivative in my formula, we need to know that this derivative exists. And here we're revolving, the surface of revolution is revolving a function in terms of x around the x-axis. We get this formula. If you have a function in terms of y with the same conditions, but we're revolving around the y-axis, we're going to have the same formula, but in terms of y. So let's try and find the surface area for these two examples. So let's start with the first one. So we always want to find the derivative first. So if this is my function, f prime would be this, and then I have a chain rule, so I need to multiply by a negative. So this is negative 1 over 2, the square root. Now, if I want to find the surface area, I just apply the formula. So we have the interval from 0 to 1/2, 2 pi, and then if you see, I want to multiply by my f of x, then the square root of 1 plus, so my f of x is just this, then the square root of 1 plus my derivative squared. Yeah. Okay, so now since I have a square root multiplied by another square root, I can get this as a one root inside of it. So I have one big square root, 1 minus x multiplied by this, which is 1 plus 1 over 4, 1 minus x dx. So now I can just distribute. Square root of 1 minus x plus 1/4. Now I have a 1 plus 1/4. I can combine them. I can use as a u sub here. I'll just do it quickly without subbing. and you do upper minus lower bound, and you get your answer. And that would be your surface area. That's it. Now for b, I have a function in terms of y. I have g of y is the square root of 9 minus y squared from 0 up to 2. We're revolving this function around the y-axis, and they're asking for the surface area, so I just apply the formula. I'll find the derivative first. So here, if I want to find the derivative, this is a chain rule. So 1/2 multiplied if you simplify, you're going to get negative y over the square root. Apply the formula for the surface area. The integral from 0 to 2 pi times your g times the square root of 1 plus the derivative squared. If you simplify, we can put these together inside of one root. Now you can distribute. So this is just the square root of 9, which is 3, so it's 6 pi, the integral from 0 to 1 du. So this is just 6 pi, 2 minus 0, which is 12 pi. So that's it. Today's section is pretty easy. You just take the formulas, apply them if you want to find the arc length or the surface area. And these are some suggested problems from section 2.4 if you want to have extra practice. And now you can do problems 16 up to 20, which is the last problems from Lumen Homework 2. If you have any questions, just email me. And that would be the end of chapter 2. Next week, we'll start talking about chapter 3, which is more methods to integrate a bit more complex functions inside of my integral. And yeah, good luck with the homework, and email me if you have any questions.